Hi, I'm Tomoki Ichikawa. Let me introduce Fresnel Microfacet BRDF, Unification of Polari-Radiometric Surface Body Reflection. Our work with Yoshiki Fukao, Shohei Nobuhara, and Nishino at Kyoto University Computer Vision Lab. We derive Fresnel Microfacet BRDF, a novel physically based BRDF model that unifies surface and body reflections by modeling the surface geometry with oriented mirror facets, and their Fresnel reflection and transmission as well as the light transport between them in the subsurface. Our principled physically based derivation also lets our model represent both radiometric and polarimetric behavior of light reflection. We show that this FMBRDF can be estimated from a single polarimetric image and also demonstrate its application to geometry recovery. Reflectance models are essential for many vision applications such as 3D reconstruction, inverse rendering, and material estimation. Physically based analytical reflectance models are particularly important for solving these inverse problems. These models assume either mirror or Lambertian microfacets, and linear combinations of these specular and diffuse models are widely used. For instance, Lambertian plus transparent for glossy surfaces. These models are, however, fundamentally physically incompatible, and a linear combination is physically implausible because the same microgeometry cannot be both mirrored and Lambertian at the same time. Our key idea is to model the surface microgeometry with a collection of oriented microfacets that mirror reflect or refract by the Fresnel law, and derive surface and body reflections from these first principles. We derive the Fresnel reflection and transmission by the oriented mirror microfacets for surface and body reflections, respectively. We also model the light transport between the microfacets in the subsurface. This physically grounded modeling also allows us to describe the polarimetric behavior of reflected light in addition to its radiometric behavior. The mirror microfacet with surface normals aligned with the half vector between the viewing and light directions reflect light to the viewer, from which we can model the surface reflection similar to the transparent model. We extend the microfacet distribution function to a generalized normal distribution, which better captures the microgeometry of a wide range of surfaces. Incident light that is not immediately reflected by the microfacet is transmitted into the subsurface of the microfacet. The transmitted light scatters through the subsurface until it is retransmitted from other microfacet into the air. This light transport occurs within a single pixel in a BRDF, and it is not a BSSRDF. We consider all combinations of the incident and outgoing point within a single pixel, and model body reflection as the sum of them. For this, we introduce a microfacet correlation function which encodes the spatial bias of the microfacet orientation distribution. We model this correlation with a 3D Formes-Fisher distribution. When kappa is small, incident light is retransmitted from microfacets oriented in any direction uniformly, resulting in an almost view-independent body reflection like Lambertian. On the other hand, when kappa is large, incident light is transported to microfacets whose normals are near that of the incident microfacet, resulting in view-dependent body reflection similar to Oren-Nyer model, but without relying on physically implausible Lambertian microfacets. As shown here, the correlation function also represents the roughness of mesogeometry. We extend the derived radiometric model to represent polarimetric reflection by modeling the polarimetric light behavior of Fresnel reflection and transmission. Surface reflection is partially polarized by the microfacet mirror reflection. Body reflection is first partially polarized by transmission, then gets depolarized by subsurface scattering, and is partially polarized again by retransmission. Based on these principles, we derive the polarimetric FMBRDF with mirror matrices. Our FMBRDF describes both the polarimetric and radiometric behaviors of light reflected by a surface. This lets us estimate the FMBRDF parameters of a surface with known geometry from a single polarimetric image captured under directional light by using intensity and DOLP of reflected light. We can use the estimated parameters to analyze and synthesize not just polarimetric, but also radiometric appearance of that surface. We experimentally validate the radiometric and polarimetric accuracies of FMBRDF on real-world surfaces. First, we examine the polarimetric accuracy by fitting the models to the dual piece of multiple polarimetric images captured under different lighting conditions. Since existing polarimetric BRDF models cannot model microfacet body reflection, they show large errors on rough surfaces. Our model accurately reproduces both the surface and body reflections for various surfaces of different roughnesses and materials. Next, we evaluate the radiometric accuracy by fitting the models to the intensity of multiple images. In contrast to existing models that fail to express the complex reflection, our model accurately represents both surface and body reflection with the generalized normal distribution function and microfacet body reflection based on the oriented mirror microfacets. We also compare the accuracy for planar samples with rough mesogeometry. We capture images while rotating the camera around the sample and compute the average intensity over the sample for each image. The results show that the microfacet correlation function enables our model to represent view-dependent body reflection. We also demonstrate the effectiveness of radiopolarimetric reflectometry with our model. We estimate the BRDF parameters from a single polarimetric image and render an image under another lighting source direction with the estimated BRDF. While the existing radiometric models fail to accurately predict the surface reflection, our model using polarization successfully reproduces both surface and body reflections. Finally, we demonstrate the application of our model to geometry recovery by jointly estimating surface normal and BRDF from multiple images captured under the classic photometric stereo setup. We use Stokes vector and DOLP for our FMBRDF and just intensity for other existing models. These results show that our polarimetric model reconstructs the surface normals most accurately and robustly. We believe our FMBRDF provides a sound foundation for radiometric and polarimetric image understanding, underlying many computer vision applications.